Hello, my name is Frank Ragon, and this is Lab 3 Circuits. The introduction and the findings from this lab was that it was to model RC circuits to understand the current and voltage relationship. Then it was to record this data from the various circuits and then calculate a time constant when a capacitor was used. Some of the findings were that the wires had 0 ohms of resistance, while the 100R resistor had 101 ohms of resistance. The computed value for the time constant was 5.88 seconds, while the experimental value of the time constant was 6 seconds. The first key concept is Kirchhoff's current law and Kirchhoff's voltage law. So Kirchhoff's current law states that the flow of current in must equal the flow of current out at a certain node, while Kirchhoff's voltage law states that all the voltages must sum to 0 within a circuit. Then the other key formula is for the time constant, as shown on the right. It can be calculated as the natural log of E, the natural log of the voltage in divided by voltage out. And then in the bottom, this shows the calculation used for series and parallel resistors. So in a series, the resistors are added together one by one to get the resistance equivalent. While in parallel, you add 1/1 divided by the resistance, all added together to get the resistance on a parallel circuit. So for the first part of the lab, the experimental setup is as shown on the right, where you have 2 batteries, 2 resistors, and 2 ammeters measuring the current. The surroundings of this circuit is none. And then for the setup, you have the 2 batteries put in series, which makes them 3 volts together. And then you put the 47 ohm resistor and the 100 ohm resistor in a series as well. And then when you measure the current, you get a 0.02 amps. So for that first circuit, here's the experimental data as it's graphed. When you're calculating the change in voltage values, from A to B, it goes up to 3 volts by adding the 1.5 battery together. And then the only 2 drops throughout the rest of it is 0.98 voltage for the 47 ohm resistor and 2.02 volts for the 100 ohm resistor. And this makes sense because then the sum of the voltage is equal to 0, as stated in Kirchhoff's voltage law. And then when we look at the total resistance, we also noted that the wires have 0 resistance, meaning that the only 2 potential voltage drop areas would be around the resistors. Then for the second part of the setup, what we have is a capacitor in a circuit with a 9-volt battery and a 20 ohm light bulb, and also was used a 10 ohm light bulb for the other part of this lab. The surroundings again were none. And then to set this up, as you can see, you have the 9-volt battery going into the light bulb and then going across the capacitor. And the first image, as you can see, the capacitor is fully charged with all the pluses and minuses showing. And then the second one, the capacitor is discharged. So as for the results from the second part of the circuit, what I saw was that the 10 ohm bulb showed that the charging time was about 14.4 seconds, while the discharging time was about 15.2 seconds. For the 20 ohm bulb, it was about double that. And in our analysis, what I saw was that the resistance was about proportional to the charging/discharging time, and both the charging and discharging time were about equal. So for the time constant, when calculating it with the data, I got that the slope of the graph was about negative 0.167, which when plugged this into the time equation, I figured out that it was 5.88 seconds for charging. While when you do it the ideal equation where you multiply the resistance by the capacitance, I got that it should have been about 6 seconds. As for the potential sources of error in this lab, since it was an online simulation with no resistance, there would be no errors with the circuit. The only issue that there could have arisen was that the recording times for the charge and discharge of the capacitor, which would have affected the time constant calculated. And then other than that, it would just be small rounding errors regarding resistance and current values. So as for the conclusion questions in this lab, if I was doing the lab in real life using an ammeter, how would it differ from the ideal simulation? So the ammeter would have a built-in resistance, meaning in the wires too, which means that the current reading would likely be lower than in the simulation, and then the voltage drop would also be greater than 0, as shown in the experiment, due to there being some resistance. And then for the second circuit, if I was doing the experiment in real life with a battery and a capacitor with no resistor in the circuit, how quickly would it charge? And then, so if we were doing this in the simulation, it would likely charge immediately. However, if it was in real life, it would take longer due to the non-calculated resistance that would also be put in the wires that aren't shown in the circuit.